Hello everyone, this is Mr. 13 Things coming at you with part of the series of the why and part of another series. All these series don't exist, just so you know, of reordering the Common Core, because while all those topics are placed in a particular order, they ignore a lot, particularly the fact that kids are computing at 3 and 4 years old. And so the standard order that the mathematicians or the math educators have put together, there's something fundamentally flawed about it, in my opinion. So that said, so this is going to be one of those questions of the why, and it came out of a conversation with one of the bright young people I know. She happens to be related to me, but this question of why do you solve for the roots? Why solve for the roots of an equation? And that always, I understand why you might do it when in fact there are some real roots for an equation. For instance, when you have a parabola that has its vertex below the x-axis and is facing up. So that I understand, but the reality is there are oft times when students are dealing with quadratic or even third order or fourth order equations when in fact there might not be a root. No, I guess with a third order equation there would kind of have to be, but there might not be a root. And so it came down to this. It's not that you should be solving for the roots very often of every equation, but you should almost always be solving for the roots of the first differential, or the derivative of the function with respect to x or with respect to time. Why is that? The concept of being at the top or the bottom of a hill is something we can all grasp from the time we are 4 years old. And so the fact that we go from 4 years old up to a very small percentage of us ever learning what the derivative means, even in terms of multivariate calculus, is a little scary. So why do we solve for roots? Well, in effect, because very often we're interested in when effectively the slope of the function is 0. Or in other words, the point when you're at a relative maximum or a relative minimum. Now, how you go about taking the first derivative of a function is not going to be covered in this video except for the most basic one, which is the formula y equals x squared. That function is a parabola facing up that has its vertex at the origin. Now, how one learns to memorize that one anyway, but how do you figure out that in fact that vertex is at the origin? Well, you take the derivative. And the derivative of x squared is 2x, because you take the exponent of the variable x squared in this case and you bring it down, so that becomes 2. And then you take the next lower power of the variable, so it's x squared becomes x to the first. So the derivative of y equals x squared dy dx is 2x. Now you set that equal to 0 and find its root. Its root becomes 0. In other words, when x is 0, y prime, or derivative of y with respect to x, is 0. That's fine. It has one low point. If you take the derivative of x cubed, first derivative, you get 2x squared. X cubed, I'm sorry, is 3x squared. And you can go through that process. If you take the derivative of x to the fifth, you'll have a number of roots. You'll have 4 roots. And that will have then 4 spots where the function effectively has a relative maximum or minimum. So that in the end is why we solve for the roots of an equation more often, or more importantly than just knowing where a function passes through the x-axis. That becomes incredibly important, especially when you start working into not just 2 dimensions but 3 dimensions and up into n space. So that's why we learn any number of ways: quadratic formula, factoring, completing the square. Not so much for solving for the roots of a function, but solving for the roots of its first derivative. So remember, derivative is the slope and the integral is the area underneath. And get that much earlier than when we give it to you, which would be at calculus level. That's me talking about the Common Core.